This is the SAM digital library page of this article. As a record of authority, this article has been quoted for 37 times and blowword for 14,000 and 1,839 times. Today we will talk about model learning. So what is model learning? Let's start with human behaviors. We always learn to use the devices or computer programming by just pressing buttons and observing the result. Especially children are very good at this and know exactly how to use a smartphone or microwave oven without even consulting a manual. So this behavior can be explained as a person interacting with the device and mentally building a state machine model to quickly discover how the devices work and how to use it. For example, this picture shows several steps to pay by using the parking meter. So we will explore this machine by pressing some buttons and observing the results when using it for the first time. It may be some mistakes, but we will eventually figure out how to use and operate this machine. In the example of parking meter, we introduced how humans learn by interacting with machines. In this author's research, he wanted to make it possible for computers to do this learning process by using some algorithms, which is called model learning. So model learning aims to construct black box state diagram models of software and hardware systems by providing inputs and observing the outputs. The design of algorithms for model learning constitutes fundamental research problems.
The basic idea of model learning is minimally adequate teacher, for short, MAT. In the MAT framework, learning is viewed as a game in which a learner has to infer the behavior of an unknown state diagram by asking queries to a teacher. The teacher knows state diagram, which in our setting is a Mallet machine. So, what is a Mallet machine? A deterministic Mallet machine can be described by the temple in the pink box. The meanings of attributes in the formula are listed in the left, and in the right there is a representation of a simple Mallet machine. So with the framework of Mallet machine, how does student learn the system? Initially, we are assuming that the system student learns can be described by the Mallet machine M. We learn this system through two types of queries. The first one is membership query. The learner asks what the output is in response to an input sequence. The teacher answers with output sequence. And the second one is equivalence query. The learner asks if a hypothesized Mallet machine H with input I and output O is correct. That is, whether H and M are equivalent. The teacher answers yes if this is the case. Otherwise, he answers no and supplies a counterexample that distinguishes H and M. Of course, the reality must be more complicated. The schematic overview of MAT is shown as graph. Two important assumptions. Firstly, the system under learning's behavior can be described by MAT. Secondly, it is always possible to bring the system back to its initial state. A membership query can now be implemented by bringing the system to its initial state and then observing the outputs generated by the system in response to the given input sequence. Equivalence query can be approximated using a conformance testing tool via a finite number of test queries. A test query asks for the response of the system to an input sequence, similar to a membership query. If one of the test queries exhibits a counter example, then the answer to the equivalence query is no. Otherwise, then answer is yes.
Hi, I'm Bruce. In recent years, model learning has been successfully applied to many practical cases in different fields. For example, regression testing in Siemens telecommunication systems, integration testing in France Telecom, automated testing in Springer's online conference, and testing requirements for Volvo technologies brake-by-wire systems. Below, I will introduce some representative research, smart cards, network protocols, and legacy software. Now is about smart cards. Chalupa and others used model learning to reverse engineer e-identifier tool, a smart card reader for online banking. In order to be able to learn the model of e-identifier tool, the author built a Lego robot controlled by a Raspberry Pi, which can operate the reader's keyboard. Next is about network protocol. For example, Fitero and others combine model learning and model checking in case study involving Linux, Windows, and a FreeBSD implementation using a TCP server and client. Model learning is used to infer models of different components, and then apply model checking to fully explore what is possible. The last part of applications is about legacy software. Legacy systems are defined large software systems that do not know what to do but are vital to the organization. Usually, the technology of these systems is outdated, the documentation is limited, and the original developers have left. In this case, Schatz and the others used model learning in Philips' development projects to support the renaissance of traditional embedded software. The project involves a newly introduced hardware component, the power control component, which is used to turn the interventional radiology system on and off. Now let's move to latest progress. Algorithms related to model learning have made significant progress, which is essential for extending these technical applications to larger systems. These include basic algorithms, register automata, etc.
Even though model learning has been applied successfully in several domains, the field is still in its infancy. There is a huge potential for applications, especially in the area of legacy control software, but more research on algorithms and tools is needed to bring model learning from the current level of academic prototypes to that of an off-the-shelf technology that can be easily applied to a large class of systems. The first challenge is predicate and operations on data. Our understanding of algorithms for learning EFSM with different predicates and operations is still limited, and there are many open questions. Using register automata learning, a stack with a finite capacity storing values from an infinite domain can be learned. Whereas using VPA learning, it is possible to learn a stack with unbounded capacity storing data values from a finite domain. From practical perspective, we need algorithms that can learn questions with unbounded capacity. The second challenge is beyond mini machines. In a mini machine, a single input always triggers a single output. In practice, however, a system may respond to an input with zero or more outputs. As a consequence, practical application of model learning is often severely restricted by the lack of expressivity of mini machines. Therefore, a lot of work is still needed to solve these problems. The third challenge is quality of models. Since the models produced by model learning algorithms
have been obtained through a finite number of tests, we can never be sure that they are correct. Nevertheless, from a practical perspective, we would like to be able to make quantitative statements about the quality of learned models. And the last challenge is opening the box. An important research challenge is to combine black box and white box model extraction techniques, and for instance, to use white box methods such as static analysis and concurrent testing to help answering equivalence queries posed by a black box learner.